Hello, my name is John Shrubin, and I'm a part of Applied Statistical Methods with Dr. Wayne Stewart. And what we're doing is going over my Project 2 presentation, Leveraging Fire Damage for City Planning. We are going to be taking a look at the fire damage data set from our textbook, and then we are going to be proving some SLR assumptions so we can use it as a linear model. Then we are going to ask a question, create an equation, and attempt to answer the question using the equation based on the linear model. About the data, we have two variables, distance and damage. The distance is how far away a home was from the fire station. The damage is how much damage was caused in a home fire. The book tells us that the samples were taken from a large suburb, but it doesn't really say anything more about it than that. For this demonstration, we're going to be assuming that it was random sampling, and the variables are both continuous versus discrete. And the question that I am asking is, as if I was a city planner, I want to know what is the optimum distance my fire stations should be apart from one another, so that I minimize the total cost of building the fire stations and the damage that the homes are going to suffer due to fires. So, the things we need to prove in order to use this as a linear model is, one, the expected value of the errors needs to be really close to zero. And then the second thing is the variance of the expected values should be constant. That's called homoscedasticity. The third is that the errors are distributed normally. And the fourth is independence. This we can't really prove without knowing that the samples were selected randomly, so that's why we are assuming it for this demo. First, we're going to take a look at the model values. For our linear model, we have two coefficients, beta naught and beta 1, and that is the beta naught is the intercept where it hits the y-axis, and the distance is beta 1, that is the slope, the rate of change as we go out in distance. Here I'm comparing two models, a linear model and a lowest model, and as you can see, the linear model fits the data points really well. The data points aren't starting to curve one way or the other. The lowest model does show a little bit of curvature starting right here, but I would say this is negligible compared to something like our spruce pine data set where the points started to curve more like a log. So that is why we are attempting to prove linearity. We're going to use this model. And the first test we're going to do is the expected value of the errors should be 0 or really close to 0. So we can for that we can take the mean of the residuals, and that gives us this number here, which is indeed pretty much close to 0 as we can get, or as we want. Next up, we can take a look at the R squared value. We get this by dividing the model sum of squares by the total sum of squares, and that'll give us a percentage, which is here in this case is 92%. What that's saying is that 92% of the variance of the data points is explained by the linear model that we're using. So it's a pretty good indicator that the distance does linearly impact the amount of damage on a home. Here for the homoscedasticity test, we are looking at a residuals versus fitted, and basically in this graph we want to see an even distribution of these data points. We don't want to see any sort of trends or shapes and for the most part they look evenly distributed around 0, which is good enough for me. So for the normality test, we're starting with a quantile plot, and with this graph what we want to see is these data points hugging this line right here. And as you can see, we have a few outliers toward the top and the bottom. This is normal for a really small data set. There's only, I think, 15 points in this one, so I think it's acceptable to assume that it's normal. Another normal test we can do is the Shapiro-Wilk test, and this would be a graph with an accept, a reject, accept, and reject region on it, and P is in the accept region when it's above 0.05, and here we got a p-value of 0.47, which means it's acceptable, and it is further evidence that this is normal data. Here we are using a Cook's plot to see what are the extreme outliers, the ones that will influence the model in an inaccurate way. And as you can see, we have one data point that is above our Cook's threshold, data point 13. And I originally thought that it would improve our linearity if I took this out. But if you take this out of the data set and rerun the R-squared calculations, you'll actually have a lower R-squared value, which would mean less of the variance is explained by the model. So I chose to leave it in, even though it is an extreme outlier. Okay, now we're at the point of actually answering our question about the optimum distance between fire stations. We're going to take into account the cost of a fire station, the probability of a fire, the size of a city in squared miles, and the number of homes it has in, so that we can get a distribution of the homes and apply that to our expected damage. We'll use predict on our linear model, and that factored with the probability will give us the expected value for the fires in the city, and then we're going to add that to what it would cost to distribute fire stations at a certain distance from one another across the city. And this is entirely dependent on our model, on our data that we got, because if we have a different data set that has a different slope, different y-intercept, we're going to get different results out of this. So to answer that question, if you look at my HTML, you'll see the actual ARD code for the total cost function, as well as a function that will graph the total cost based on the parameters that we talked about. And in this instant, I'm going to be running the function on Moore, Norman, and Oklahoma City to see what kind of different results we get. The values for the number of homes and the size of the city is just basic census data. And then I made up some values for how much it would cost to build a fire station. And then the probability of having a fire is generally considered to be 1%, although this would vary from region to region. And I think it would be lower in Oklahoma, but we're going to be sticking with 1% for now. So here's Moore's result. We gave them a high cost of a fire department, a small area, and they have pretty small amount of homes, so they have low home distribution. This their optimum distance was at 5 miles apart. This one was kind of hard to illustrate because of how small the city was. They can't get any advantage by building them further apart because they'd be outside of city limits. For Norman, I gave them a low cost for fire department, a medium area, and a lot of homes. And they actually had an optimum distance that was smaller than 5 miles because of how cheap their fire departments were. They're going to save money if they build more of them. And then for Oklahoma City, we have a medium cost, large area, and a lot of homes, very high home distribution. And this one differs because they were able to extend their distance beyond 5 miles, and they're sitting at 6.3 miles. And if they built them closer together, they would be spending more money. So it worked out pretty well for Oklahoma City. And we're just going over the results again. Norman had a tighter distance because of how cheap their stations were. Moore's graph was step-like due to the small area, low number of homes, and Oklahoma City had the most optimum distance, stretching over 5 miles. Then I put my functions in a Shiny app so that I could manipulate the inputs easier. And here I just want to show you the difference between a low probability of fire and a high one. So I kept the other parameters the same and just changed probability. So here at a very low probability, it'll allow you to build your stations further apart. And then if you crank the probability up, this is unrealistic, but it's just for illustration purposes. You will actually be saving money if you build your stations closer together, more like the Norman situation. So I thought that was pretty cool. Without the linear model that we got from the data, we wouldn't be able to answer this question accurately. So that's why we made the linear model. And then just some ways to improve the experiment. We could get a larger data set so we can be more confident that it was actually linear. I intuitively thinking, I thought that it would be exponential because as a fire spreads, the new fire that it creates is creating more fire, and I thought it would be a more exponential trend, but apparently not. And then also I could improve my total cost function by factoring in the operating costs over time. Right now it's just a flat rate for the initial build, but